All right. Let's see, does it work?
Let me see.
All right, I leave the floor to you.
Perfect. Good morning, everyone. Can you guys hear me? Okay. Thanks for having me. My name is Pranav Sanke. I'm part of the Spatial Statistics group at Oak Ridge National Lab. And here I'm here to present Jesse Pyburn's work on embedding geographic concepts of a place into probabilistic modeling of how many people are in a building at a given hour anywhere in the world. So let's start with motivating the problem. Emergency response, energy grid modeling, disaster logistics, all depend on occupancy rates. This is the number of people in a 1,000 square foot area. To address this, we propose a framework called population density tables. As the name suggests, it contains probability density of the number of people per square foot of everywhere for every building, any time of the world. So let's start with a broad matrix of ambient occupancy. For example, if you look at restaurants in Russia, we might have an overall ambient occupancy of 11.5 people in a building of 1,000 square foot. And if we plot that across a week, across a typical week, we get something like this. But this is just a single number, and it's inefficient. It's insufficient. The true scientific task is much more deeper. That is, given that aggregate number of 11.5, how can we estimate the underlying distribution that details hourly occupancy curve, where the average is still that 11.5 number, but we get to discover a lot more activity. That is intraday, intra-week. So this is where our interdisciplinary approach begins. We realize that simple fitting of mathematical function is not enough because human behavior is inherently tied to the location that they're in. The rhythms of activity is not universal. They're specific to a place, the task or activity that is conducted there. And our goal is to build the model that can capture this sort of place-based temporal patterns. So you can see here we have a cafe in New Orleans. And if we just plot all the restaurants in New Orleans, we see some sort of temporal pattern emerge. So for our project, we consider 62 different types of places, something like a church, government offices, parks, restaurants, supermarkets, and 57 others. Each line in that plot represents a POI, a place of interest, and the darker line is just the average over all those places. Again, as we can see, different places have different rhythms. For example, this is Lakeshore Park in Knoxville, where I'm from. And you can see it's kind of busy throughout the week. That bold line is the one that's indicating it, especially on the Sundays. Now, this is Victor Ash Park, less than 10 miles away from that park. And you will see the weekends are a lot more busier, the weekdays aren't. These are both parks in like a 10-kilometer vicinity, but there's differences in the way the activities occur over there. Similarly, a church in Knoxville is busy on the Sundays for Sunday Mass, but a church in Sri Lanka might also have some sort of activity happening during Sundays. Government building, this one is a Social Security Administration office in Knoxville, and it's only open from Monday through Friday, and it's closed on the weekends. But if you look at a government building in Sri Lanka, because of cultural differences, or like Bangladesh, cultural differences, their weekends are different. It's Friday and Saturday, so you see a different pattern there. Papa John's, great place. Pillar of Society of Knoxville. You'll see that the weekends are a lot more busier starting Friday, but a Papa John's in South Korea is just busy throughout the week. So, looking at all that, The constraints here are that we want to capture this cross-cultural heterogeneity, quantify uncertainty, and also be useful in data poor or data absent location. In order to do that, we have these standard approaches where we can fit one of these models, and they'll do great. Only if we have good data, though. Our problem is that we have bad data. We barely have any data. But we might have some good theory. This is where the concept of place comes into play. It turns out that there's deep literature on what a place is and the temporality of a place. We want to leverage this qualitative concept of place and then tie it to the parameters of a Dirichlet distribution, which looks something like this. So the rhythm itself is modeled by a Dirichlet distribution. Mu is just a mean vector of the activity pattern. Affordance or phi is our precision parameter representing how tightly a POI conforms to the mean activity, which means how much of a Papa John's is it a restaurant or not. And then finally, CRPS is just the quality of it. For this project, we leverage Google Popular Times. It's publicly available, has broad global coverage, so it's a good starting point. Our model is a Bayesian Dirichlet regression, and the output that we're expecting is an hourly occupancy rate that is detailed just like that. So a place's function in society is a constructed role. It emerges on how we use that place, the activity that is performed over there, and not just the label that is imposed on it. So essentially, if we reframe this into mathematical terms, what we want to know is, to what extent does a place observe temporal behavior aligns with the distribution of the expected label? The tool that we use to do that is CRPS, which is the continuous rank probability score, where we compute the CRPS between the observed hourly value and the hours beta marginal. And then we just average it over 168 hours of the week. Here we can take a look at it in practice for Taipei's tourist attractions and Knoxville's drugstores. So when we go pull an individual POI from which has the single highest CRPS or the worst functional fit, what we find is, in Taipei, the least typical tourist attraction turns out to be a jewelry store that's only open on the weekends. Very different from what the rest of the category is. And for Knoxville drugstore, our drugstore is closed on the weekends, located inside like a strip mall. Again, technically a drugstore, but behaviorally an outlier. And CRPS helps us surface these type of atypical cases automatically, at scale, again, everywhere. Now let's walk through like an end-to-end example where we collected Google Popular Time data for around 5,200 airports worldwide. And we sourced it against the R Airports database that has over 85,000 airports globally. And we wanted to update the airport occupancy rates. As an example, and again, this work was conducted before any of the troubles in the Middle East, we're just looking at 4 Iranian airports, with each one of them having their own weekly popularity curve, and it's fairly noisy. We see that when we run the same Bayesian Dirichlet regression pipeline, we get our Google Popular Times in, Dirichlet regression model, and out comes the temporal activity distribution. But the temporal activity distribution isn't the occupancy density. Occupancy density is an actual number of people per square foot. So we build an allocation model here that combines the Dirichlet-based shape that we first derived, and we separate it based on open and close. So if a government office is closed, we would basically have no people there. It's a completely different thing from if it was operational. So in order to do that, we just weigh the Dirichlet distribution by the open-close probabilities. And that's when we are able to produce our final outputs. Here you can see, again, going back to our Iranian airports, we have daytime distribution in green and the nighttime distribution in blue. these are ambient densities. And then the Dirichlet hourly temporal activity that we derived is on the right. If we had to combine these two, we get an updated hourly occupancy density estimate. Once we combine them, the full probability, full posterior, is what we get here. If you notice, there's that green line, and then there's a blue line, the straight lines that are cutting across. Those are our ambient occupancy rate for open and closed building activity periods. You can see how there's so much of intraday variance and intra-week variance, even within our model. Our model overpredicts. In certain cases, when things are open, activities are allowed, and it underpredicts when something or a building is closed. Well, we can see why there's so many limitations to our work, because the assumption of a stable week itself is there's no typical week. We don't really have, there's a lot of variance between holidays, global events, so on and so forth. There's seasonal things. Second, the verification and validation at global scale is genuinely hard. Ground truth for occupancy data just at this resolution basically does not exist. We're attempting to create this. And finally, we're really relying on Google Popular Times as a single data source, which has its own coverage bias, and hence the kind of predictions that we get can be rough on the edges. So with all of these limitations, our future work involves using more covariates, bringing in other variables that can support where things are lacking with the data itself, and just trying more AOIs and POIs just to test the robustness of the approach itself. Yes, this is my talk. Thank you, and if you guys have any questions, please feel free.
We have a question there, Brian. Oh, it's dangerous.
I think it's soft. Yes. Thanks for the talk. So obviously you mentioned a few other things that this sort of data would be useful in terms of disaster preparedness and stuff like that. But for the specific energy planning purpose, it feels like I'm curious why you would be modeling occupancy versus just energy uses in particular, because like a data center that has 5 people in it might use more electricity than a church that has 1,000. Right. And so like, how does that, do you also account for the energy usage of a typical place per occupant, I guess?
I guess the idea here is to downstream connect those two things, these two concepts. 80% of built environment is residential. And if you want to create a new subdivision, start a new little community, you're basically building 80% of the buildings that are residential. So just knowing the amount of people in there, and hence the kind of energy they might draw, could be useful. It could be one of the covariates that can help you do the downstream task, might not be the end-all goal. So yeah, it's a great tool while planning for these things, urban planning or energy grids. But yeah, just this one source cannot be just a reliable, yeah.
Thanks.
Charles?
Thanks for the very clear presentation. I was wondering if you could go back to your last slide about occupancy in the airport. So this is something I see in many models, which is, right, there's a certain lack of smoothness, especially if I look at Monday, and I kind of see these dents that appear both in the median and the posterior intervals. And I'm curious, right? Obviously, the model is not smoothing these out. Mm-hmm. So how much do we believe these dents to be a signal as opposed to noise?
So with airports, there's this caveat that there could be a lot of red-eye flights. So during the evening time, you could see like a surge in like popularity all of a sudden. Mm-hmm. And you can find these weird sort of curves that just come up, these things that pop up, which might throw off your model, unless it's accounted for actively. In our model, we're trying to do so, but as you can tell, it's still kind of over-predicting a lot of times.
So you think that these are over-predictions? So for example, the dent we have slightly after noon on Monday, or could this actually be because the flight schedule is such that actually.
And again, because validation is so difficult, coming up with an approximate number for this problem at this resolution is something that we've decided should be good enough. Yeah.
No, it's fascinating. To me, it's fascinating that Monday is just less smooth. I mean, I guess that makes sense, but than other days of the week.
Right.
All right. Do we have any other questions?
Thanks. That was really interesting. You sort of talked about how there's no typical week worldwide, but there's also this separate issue of sort of within year events. And so I remember seeing a lot of work by EDF Energy looking at forecasting load in France and sort of things like, you know, French national holidays that are a bit more regulated than in other countries. Sort of that individual level, like this particular area has a holiday or this particular area does this thing at this time of year. Do you have a sense of how you can accumulate that kind of knowledge into this kind of model, or is it really just an average week per place?
Yeah, and I guess that's where the issue with the typical week is a big problem, is that there's just no regularity. There's a lot of seasonality to these things, but again, you cannot really just expect that from this one single data source. If we were able to bring in a covariate that will tell you, hey, there's like FIFA World Cup happening in the US, so things are going to be different. And just bringing in that covariate should be able to help us. There are efforts towards that, but in this presentation, we're just limiting it to this.
Thanks.
All right, do we have any more questions? I don't see any more questions, so I suggest we have a last applause. And then it's coffee right now outside.